Right, in this video we're going to start talking about transformations of graphs, and the transformation we're going to talk about this time is vertical shifts of graphs. Right, there are many different rules for different types of transformations, and I'll be doing a video for each one of those rules. So this one just covers vertical shifts. If you're looking for other types of transformations or just transformations in general, watch all the videos that I do on these and you'll get like the full picture. Trying to do all of the rules for the transformations in one video, I mean the whole thing would be just way too long. So we're going to do them one by one, each of the different rules, and then maybe I'll do one video where I kind of quickly summarize them all and put them all together. But this one we're just talking about the vertical shifts of graphs. Alright, so assuming that c is greater than 0. So c is some constant, it's a number, and we're saying here that it's a positive number. Right? So if I want to graph the function y equals f of x plus c, I shift the graph of y equals f of x up c units. Right? So if I have f of x, some function that I already know what the graph looks like, y equals f of x. If I know what that graph looks like, and then I want to graph f of x plus c, right? So that same function with just some number added on the end of it, well, I take the graph of that one that I know, and I just move it up by whatever that number is. So like if I add 5 to the end of the function, I just take that graph and I move the whole thing up 5 units. That's what we refer to as a shift in the graph, in this case a vertical shift, right? Because up and down is in the vertical direction, right? On the other hand, if that number is being subtracted, if I graph y equals f of x minus c, I shift the graph of y equals f of x down c units. Alright, so once again, if I know what the graph of y equals f of x looks like, and then I graph f of x minus c, right? So when I subtract a number from it, so let's say I have that function f of x minus 2, right? I take the graph of y equals f of x and I move all the points down 2 units, and that gives me the graph of y equals f of x minus c. Alright, so those are the rules for a vertical shift of the graph. When I add a number outside of the parent function, I go up c units. When I subtract a number on the outside, I go down by that many units. All right, so the f of x here, the graph, the function whose graph we know, we call that the parent function. All right, and I did a video where I reviewed the graphs of 6 different parent functions and some of the key points on those graphs. So if you haven't seen that yet, you might want to check that out so you have some familiarity with the parent functions that you should already know what the graphs of those look like. All right, so we call that the parent function. So the basic rule here for vertical shifts, just to break it down, hopefully as simply as I possibly can, right? So when you add or subtract a number outside of the parent function, right, that f of x minus c, that f of x plus c, that's not affecting the parent function itself, right? That f of x there is still intact. That plus c or that minus c is happening outside of the parent function. So when we add or subtract a number outside the parent function, really what we're doing is we're adding or subtracting that number to the y value. Right here, y equals f of x. Here, y equals f of x minus c. Right, so I'm basically subtracting that number from the y coordinate of all the points on my graph. Right, so if I add or subtract a number to the y value or to the y coordinates of my graph, well, that's going to move the graph up or down, right? Because the y coordinate is the one that measures the vertical position of your graph. Right, so if I have a vertical position up here and I subtract from it, well, that's going to move it downward. Right, so just like with a lot of other things in math, if you memorize what the rule is, that's great. But if you understand why the rule is what it is, then you don't have to memorize the rules. You just understand it, and you can just go ahead and do it when the time comes. Right? So again, adding or subtracting outside of the parent function is affecting the y coordinate, and I'm just adding or subtracting a number to the y coordinates of all the points on my graph. That's shifting the graph up or down. And of course, when I add a number to the y coordinate, well, that makes the y coordinate bigger, so it shifts it up. If I subtract a number from the y coordinate, that makes it smaller, it shifts it down. Right? So again, if you get that understanding, it all just kind of makes sense as far as how this all works. All right, so those are the rules for the vertical shifts. What I'm going to do is pause the recording and erase this and put up a couple of examples where we actually draw the graphs of functions using these rules. Alright, so I put a couple of examples up here. We're going to draw the graphs of g of x equals x squared plus 3, and then also h of x equals x squared minus 2. Alright, so to do these, we're going to use the graph of the parent function for these two. So the first step in using transformations in order to graph a function is to identify what the parent function is. Right? And again, I did a video about 6 different parent functions and what those graphs look like. So if you haven't seen that yet, you should definitely watch that video and familiarize yourself with the different parent functions that we'll be using. But this one, the x squared plus 3 and the x squared minus 2, hopefully is pretty obvious to you that the parent function there would be x squared, right? The quadratic function, right? So I'm going to use the function of y equals x squared to figure out what the graphs of x squared plus 3 and x squared minus 2 are going to look like. Right, so the first thing here that I'm going to do is I'm going to actually graph the parent function. Now, when you're doing these types of problems, you don't always have to graph the parent function first. As long as you know what the parent function looks like and you know the points on that graph, you can just go ahead and draw the graphs of these two. But just for the purposes of explaining it and showing you what's going on, I'm going to graph the parent function first and then graph these other two as well. And we'll have all three of them up here on one single graph. All right, so the graph of the parent function, right, y equals x squared, is a parabola, and some of the key points on that parabola are 0, 0, 1, 1, 2, 4. Trying to make sure I put these all in the right spot. So 2, 4, right, negative 1, negative 1, and then negative 2, 4. All right, so if I draw my graph going through there, there's my graph of y equals x squared. That's my parent function. All right, and again, that's one of those ones that you should know. You should know what the graph of y equals x squared looks like. You should know several of the points that are on that graph. And if you forget what those points are, like I said in that other video that I did, like if I forget the point for x equals 2, well, just plug in x equals 2. 2 squared equals 4, so it's the point 2 comma 4, right? So you can do that with any of those other points as well. That should be negative 1, positive 1, not negative 1, negative 1. Okay, so that's the graph of our parent function. So now I have g of x equals x squared plus 3. I'm going to use this blue graph of the parent function here to graph x squared plus 3. All right, so the first thing when you're using a parent function to graph a transformation, once you know what that parent function looks like, the next thing is what type of transformation do I have? Right, and in this case, when I have that plus 3 added outside of the parent function, right, the x squared is still there, right? We're not really touching that x squared. That plus 3 is being added separate from the x squared. When I have a number added or subtracted separate from the parent function, it's affecting the y coordinates, and that's the vertical direction. Right, so for g of x equals x squared plus 3, if I'm adding a number here, basically what I'm doing is I'm taking all the y coordinates that I have on all these points, and I'm adding 3 to each one of those y coordinates. Right? That's why it's important on the parent functions to know the coordinates for some of these points. Right? Because then for x squared plus 3, well, it's outside the parent function. I have to add 3 to every y value. I just add 3 to each y value and plot those new points, and that's going to give me my graph of x squared plus 3. Right? So let's do that. So negative 2, 4, when I add 3 to the y value, I'm going to get the point negative 2, 7. Negative 1, 1, when I add 3 to that y value, I'm going to have the point negative 1, 4. Right, 0, 0, when I add 3 to that y value, I'm going to get the point 0, 3. Right, 1, 1, add 3 to the y value, I get 1, 4. Right, 2, 4, add 3 to the y value, and I get 2, 7. And if I now connect those points, that's my graph of y equals x squared plus 3. Or g of x equals x squared plus 3. Right, so the graphs of the parent functions, or the transformations of the functions, they have the exact same shape. And if I had drawn this a little more to scale, and if I could draw nice lines and everything, you would see that these two have the exact same shape. It's just I take that blue graph and I move the entire thing up 3 units. That gives me the graph of x squared plus 3. All right, so that's how we use transformations of functions to draw a graph. If I know the points, the coordinates for those points on the parent function, I just have to change the numbers. In this case, by adding 3 to the y coordinates, that gives me the new graph. All right, and when I say that the thing is happening outside the parent function, like x squared plus 3, I said that plus 3 is happening outside of the parent function. Just to give you like a counter example of something happening inside the parent function, if I had something like this, like y equals x plus 3 squared, right? The parent function for this is still x squared. It's still the quadratic function because that x there is being raised to the second power. But now that plus 3 is happening inside that parent function, right? It's in the parentheses with the x, whereas this x squared plus 3, that plus 3 is happening outside of the parent function, right? And I'll do another video where I show you what happens when we have that plus 3 added inside as opposed to outside the parent function. Is obviously it's going to do something different than what happened here. right? So I just wanted to clear that up. I keep saying like the plus 3 or the minus 2 is outside the parent function. This would be inside the parent function, right? The plus 3 is being squared along with the x. Here, just the x is being squared, and then that plus 3 gets added onto it. Right, so when the things are happening outside of the parent function, again, it's only affecting the y coordinate, right? Nothing here is messing with the x, but once I do that x squared, then I'm adding 3. That's why, like when I have the point, 1, 1 changes to 1, 4. Well, if I plug in x equals 1, 1 squared still equals 1, but now I'm adding 3 to that, which gives me the output not of 1, but of 4. Right? That's why when I have that plus 3 outside of the parent function, really all I'm doing is adding 3 to each one of my y coordinates to get my new points, and that's shifting my graph up 3 units. All right, again, like I said a few minutes ago, if you understand why these rules are what they are, why does plus 3 here mean move it upwards, you don't have to memorize the rule, you just understand, okay, so I have my parent function, when I do plus 3, that takes my y coordinate, I plus 3, I actually add 3 to all of those, and that gives me my new graph. All right? Same idea for this one. H of x equals x squared minus 2. Right? So again, the parent function is y equals x squared, the blue one here. So I go back to that original one that I graphed, the y equals x squared, and now I have x squared minus 2. Right? So I'm taking all my y coordinates now, and I'm subtracting 2 from each one of those y coordinates. All right, so 0, 0 is going to go down to 0, negative 2. Right? I take my y coordinate, I subtract 2 because I have that minus 2, again, outside of the parent function, that's affecting my y. So I bring that point down to the point 1, 1. I subtract 2 from the y coordinate. That's going to be the point 1, negative 1. Right? Negative 1, 1. Also subtract 2. That brings it down 2 units. So that's the point negative 1, negative 1. 2, 4. I bring that down 2 units. Right? Or I subtract 2 from the y coordinate. There's a couple ways to think about it. You can think about it as I'm literally subtracting 2 from every one of those y coordinates that I have up here in blue. The other way to think about it is I'm taking each one of those points and I'm lowering it 2 units. Right? They both do the same thing to the graph as far as bringing it down 2 units. Right? And this one here, 2, 4, when I subtract 2 from that y coordinate, it brings it down 2 and gives me the point 2, 2. And this one over here, again, I put a negative when I shouldn't have. This was negative 2, positive 2. Right? Now if I connect all those black points up here, that gives me the graph of y equals x squared minus 2, or h of x equals x squared minus 2. All right, so once again, if I had drawn these more to scale, all 3 of those graphs have the exact same shape. Right? The relationship between all these points is the same for each one. Right? From your vertex, you move over 1 and up 1 to get your other points. Right? Over 1 and up 1 to get your other points. To get the next point, you move over from this one, over 1 and then up 3 more, right? Over 1 and then up 3 more, that gets you your next point, right? So the points on each individual graph all have that same relationship with the points on the same graph, which is why all 3 of these have the exact same shape. It's just that when I have that plus 3, that minus 2, it takes that same shape and slides the whole thing up 3 or down 2, right? We get the same shape, just in a different position. Right, so that's a couple examples of doing vertical shifts of graphs. Right, for this one, we just use the parent function, y equals x squared, but the same rule applies no matter what the parent function is, right? If the parent function was the absolute value function, which is that v shape, if I had the absolute value of x and then plus 3 on the outside, it takes that v and just goes up 3. If it was the absolute value of x and then minus 2 on the outside, it takes that v shape and just drops it down 2. Right? It doesn't matter what the parent function is. The rule for plus 3 and minus 2 outside of that function always does the same thing. It's going to give you that vertical shift. So again, it's important to know, those parent functions and what the graphs look like, because when you sit down to do a homework problem, it might not be x squared plus 3. It might be x cubed plus 3. Right? So you need to know what the graph of x cubed looks like, and then translate the points on that graph by adding 3 to all the y values to do similar to what we did here. All right. So those are the vertical shifts. Again, that's just one of the rules for transformations of functions. I'm making some other videos, and so make sure you check those out as well to get all the other rules for the transformations of graphs, because there are several rules that you need to be aware of when you're doing this type of thing.